Here's a question that has ended more senior engineering interviews than almost any other, and it's only 5 words long. Design me a system like ChatGPT. Simple to ask, brutal to answer. Because the moment you start drawing boxes, the interviewer starts asking the questions that separate people who've used LLMs from people who understand how they run at scale. How do you serve a model that needs 80 gigabytes of GPU memory to 1 million people at once? What happens to the request that arrives while the GPU is busy? Why does the first word take a second to appear, but the rest stream out instantly? Here's what most candidates get wrong. They think a system design interview is about knowing the right answer. It isn't. It's about defending your trade-offs. So at every decision, I'll show you the options, what each one costs, and how to argue for the one you pick. That's the skill that gets the offer. And we'll do it inside a framework that works for any system design interview. 6 steps: requirements, the API, a quick estimate, high-level design, the deep dive, where the real engineering lives, and the wrap-up. Keep that in the corner of your eye. That structure alone will make you look senior before you've said anything clever. Let's go. Framework step 1, requirements. And the rule that quietly fails most candidates: do not touch the architecture until you understand what you're building. Jumping to, let's add a load balancer before you know what you're balancing is the fastest way to look junior. Functional requirements, keep it tight. A user sends a prompt. We stream back a response token by token. Conversations are multi-turn. Context carries across messages. And say what you're not building. No training, no fine-tuning, no safety filtering today. Naming your scope is itself a senior signal. Now the non-functional requirements, where the real design lives. And we quantify, because vague requirements produce vague designs. Scale: 1 million daily users, 20 messages each, is 20 million messages a day. Peak is spiky. Call it 5 times average. Roughly 1 to 2,000 requests per second. Latency, and here's the subtlety most people miss. There are 2 latency numbers, and they fight each other. Time to first token. How long until words start appearing? Target, under a second. And inter-token latency, how fast they stream after that. Target, about 50 milliseconds per token. Here's the tension. To keep GPUs efficient, we batch many users together, but bigger batches make each user's tokens come slower. Throughput and latency are in direct conflict. The entire design is negotiating that trade-off. And cost? The constraint that makes this problem unique. A single high-end GPU runs $2 to $4 an hour, $30,000 a year, and you need thousands of them. So, just add machines doesn't just get expensive, it becomes the entire business. A GPU at 30% utilization is most of a $30,000 asset set on fire. Framework step 2, the API. A step most candidates skip, which is itself a red flag. Before boxes, define the interface. It's fast, and it forces a decision that shapes the whole system. The endpoint is simple. Something like post/v1/chat. The request carries the conversation and a few parameters. The interesting part is the response. How do you return something generated token by token over several seconds? 3 options. Option 1. Plain buffered response. Wait for all tokens, then return the whole thing. Dead simple. But the user stares at a spinner for the full generation. For a long answer, that's seconds of nothing. Rejected. Option 2. WebSockets. Full duplex, great for back and forth, but it's overkill. Generation is one-directional, server to client, and WebSockets add connection state we don't need. Option 3. server-sent events, a single, long-lived HTTP response that streams tokens as they're produced. One directional, which is exactly our shape, works over plain HTTP, auto-reconnect built in. This is what real LLM APIs use, the crisp answer SSE, because generation is unidirectional streaming and it's simpler than WebSockets. And two details that reveal depth. Statefulness, do we resend the whole conversation each turn or store it on the server? And back pressure, the model can generate faster than a slow client receives. Flag both now. We'll see the KV cache make conversations implicitly stateful later, and that's a tension we'll have to resolve. Framework Step 4, High-Level Design. Let's draw what everyone draws first. A user sends a request. It hits a web server. The web server forwards it to a GPU with the model loaded. The GPU generates the answer and streams it back. Clean, simple, and it collapses almost immediately. Here's the crack, and it comes from how a language model actually generates. It doesn't produce the answer all at once. It produces one token at a time, and each token needs a full pass through the model. A 200-token answer means 200 sequential steps on that GPU. Now watch what that does to our design. While the GPU spends a full second generating one user's answer, every other request just waits in line. One GPU, one user at a time. Watch the queue back up. So do the math. If a response takes about a second, one GPU serves roughly one request per second. We need 1 to 2,000 per second. That's up to 2,000 GPUs, each serving a single user at a time, at $3 an hour. $50,000 to $100,000 a day, and most of those GPUs are barely working. The naive design fails on the one thing we said matters most, and it hands us the first real insight. The bottleneck in serving a language model is not the network, not the database, not the CPU. It's keeping an incredibly expensive GPU busy. Everything we build from here serves that one goal. To design this well, you have to understand one number, because every optimization in this entire field is a consequence of it. It's called arithmetic intensity, the ratio of math operations performed to bytes read from memory, ops per byte. Here's why it matters. A modern GPU can do about 1,000 trillion operations per second, but it can only pull a few terabytes per second out of its memory. Divide those, and you get the GPU's break-even ratio, very roughly a few hundred ops per byte. If your workload does more math per byte than that, you're compute-bound. The GPU is working at full tilt. If you do less, you're memory-bound. The compute units sit idle, starving, waiting for data. That's the roofline. Now watch generations split cleanly across that line into two phases with opposite physics. Phase 1, Prefill. You hand the model the whole prompt at once. It processes every token in parallel. Big matrix multiplications, tons of math per byte. High arithmetic intensity, compute-bound. A large model hits over 90% GPU utilization here. This is why time to first token grows with prompt length. Phase 2, Decode. Now it generates one token at a time. To make a single token, the GPU must load all the model's weights, tens of gigabytes, out of memory, to do math on just one token's worth of data. Almost no math per byte. Rock-bottom arithmetic intensity, memory-bound. That same GPU that was at 90% craters to 30. The compute units are literally idle, waiting on memory. Sit with that, because it's the crux of the whole system. Prefill and decode want opposite things from the hardware, yet the naive design runs both on the same GPU. During decode, which is most of a request's life, you're paying for compute you can't use. Remember that. Later, it becomes the single biggest cost lever in modern serving. Let's open up that GPU box because what's inside changes everything. When the model generates each token, it needs to look back at every token before it. Naively, that means rereading the entire sequence for every single token. Quadratic waste. The fix is the first piece of magic, the KV cache. As the model processes each token, it stores that token's key and value state in GPU memory. So token 201 doesn't recompute tokens 1 through 200. It just reads their cached state. The KV cache is a classic space-for-time trade-off. We spend precious GPU memory to avoid recomputation, and that memory cost is brutal. The cache for a single long conversation can be several gigabytes, and it grows with every token. On an 80-gigabyte GPU, where the weights already eat 40 to 70, you might have only 10 to 30 gigabytes left for all users' caches combined. So the real resource you're managing isn't CPU or even GPU compute. It's GPU memory. And here's a second-order consequence most candidates miss. Because decode is memory-bound, and the cache is a big part of what gets read every token. Shrinking the cache directly speeds up decode, which is exactly why modern models change their attention design. Multi-head attention, the original, gives every head its own keys and values. Biggest cache. Multi-query attention makes all heads share one. Cache shrinks about 10 times, but quality can dip. And grouped query attention is the pragmatic middle. Groups of heads share. Most production models use it because it recovers nearly all the quality at a fraction of the cache. That's the sweet spot on the quality versus memory curve. And flash attention belongs here too. It computes attention without ever writing the giant intermediate matrix to slow memory, tiling the work in fast on-chip memory instead. It doesn't change the answer, it changes the memory traffic. And since we're memory-bound, that directly buys speed. Now the centerpiece. We said decode is memory-bound, with compute to spare. That idle compute is the opportunity. Process many users' token steps at once. That's batching. But how you batch is everything. 3 options. Option A, no batching, 1 request per GPU. Simplest. Utilization, 20 to 30%. Cost, catastrophic. We already rejected it. Option B, static batching. Collect 16 requests, run them together, wait for all 16 to finish, then take the next 16. Better. But here's the flaw. Request A wants 10 tokens, request B wants 500. A finishes almost instantly, and its slot sits idle for the 10 seconds B keeps going. With mixed response lengths, which is reality, you waste a huge fraction of your capacity waiting for the slowest one. Option C, continuous batching. The breakthrough. The batch is a rolling set of slots. The instant any request finishes, its slot is immediately filled by the next request in the queue. The GPU never waits for the slowest. The batch stays full every single token step. Why C wins and what it costs. Continuous batching takes utilization from 30% to 80 or 90. Often a 3 to 5 times throughput gain on the same hardware. 3 to 5 times cheaper per request. The cost is complexity. The scheduler now manages a dynamic batch and cache slots that come and go, which is why you don't build it from scratch. You stand on frameworks like VLLM. Naming build versus buy with a reason is a senior move. There's one more, paged KV cache. The cache is variable length and comes and goes as requests join and leave. That fragments GPU memory. The fix mirrors operating system virtual memory. Store the cache in fixed size pages, so it never fragments and packs tightly. That's what lets you push batch sizes higher, which pushes utilization higher. Memory management is throughput here. And two frontier moves. Chunked prefill. Break a long prefill into pieces and interleave them with decode steps so a big new request doesn't stall everyone's streaming. And speculative decoding, a small draft model guesses the next few tokens. The big model verifies them all in one parallel pass. 2 to 3 times faster decode, identical quality. Why is it nearly free? Because decode is memory bound, and verification uses the spare compute we already had. Now the move that instantly separates a strong candidate. Before scaling out, estimate. Turn requirements into an actual GPU count with back-of-envelope math. I'll keep the numbers round. The point is the method. Step 1. Model memory. A 70 billion parameter model, 2 bytes each, is 140 gigabytes just for weights. An H100 has 80, so the model doesn't even fit on one GPU. We need at least 2, realistically 4. That's not a choice, it's a hard flaw. Step 2. Cache per user. For a 70 billion model with grouped query attention, the cache is roughly 0.3 megabytes per token. A 4,000 token conversation is about 1.3 gigabytes per user. Step 3. Concurrent users run on 4 100s, 320 gigabytes. Weights eat 140. Leave a margin. That leaves roughly 150 gigabytes for cache. Divide by 1.3, about 100 concurrent users per 4 GPU replica, and notice what capped us at 100. Memory, not compute. This is exactly why everything we did fought for cache memory. Grouped query attention, paged cache, quantization. Every one of them is really buying concurrency. Step 4. Turn that into fleet size. Each user streams about 30 tokens a second. A 500 token answer, 16 seconds per request. A replica with 100 users completes roughly 6 requests a second. We need up to 2,000. 2,000 divided by 6 is over 300 replicas times 4 GPUs, well over 1,000 GPUs. Step 5. The punchline. At $3 an hour, 1,300 GPUs is roughly $4 million a month, just in compute. Now every optimization has a dollar sign. Continuous batching, disaggregation, stacked. They're the difference between 4 million and under 1. This is why we obsessed over utilization. The estimate makes the stakes literal. 1 GPU is efficient now. 1 million users need thousands. This is a distributed systems problem, and the trade-offs get sharper. First, the payoff of that loop I planted. Prefill is compute-bound, decode is memory-bound, and running both on the same GPU means during decode you pay for compute you can't use. The modern answer is to stop running them on the same machines. Split the fleet into a prefill pool and a decode pool. A request hits a prefill GPU. Short, compute-heavy, fills the cache. Then the cache is handed off over the network to a decode GPU. Long, memory-heavy, streams the tokens. Why it wins? You can size each independently and even use cheaper hardware for the decode pool. Reported results: 2 to 4 times better cost. What it costs? You must move gigabytes of cache between nodes fast, plus a lot more operational complexity. The honest line: start collocated, disaggregate once scale justifies it. Next, the model doesn't fit on one GPU. Tensor parallelism splits each layer's math across GPUs wired by a fast interconnect. Great within one node, too chatty across the network. Pipeline parallelism puts different layers on different GPUs, less bandwidth, but pipeline bubbles where GPUs idle. The pick: tensor parallelism inside a node, 4 to 8 GPUs acting as one replica, then replicate that replica into a fleet. Now routing, and the naive answer is wrong, which is what interviewers probe. A normal load balancer sends each request to the least busy replica. But remember the cache. A user mid-conversation has their cache sitting in one specific replica's memory. Route them elsewhere, and it rebuilds gigabytes from scratch. So we want cache-aware routing, sticky to the replica that already holds the conversation. And the queue is not a dumb FIFO. Prioritize paid users first or short requests first to protect latency, but add aging so nothing starves. Queue depth is also your auto-scaling signal. And auto-scaling has a twist. GPUs don't cold start in seconds. Loading tens of gigabytes of weights takes minutes. So you scale on leading signals and keep warm spare capacity, paying for idle GPUs to protect latency. You've got a working, scalable design. Now the interviewer stress tests it. These are the follow-ups where offers are won or lost, and everyone is a trade-off, not a fact to recite. A request fails midstream. What happens? Generation is stateful, so you can't blindly retry a half-finished stream. You can checkpoint the generated tokens and resume, or let the client reconnect and continue, or just restart and eat the cost of regenerating. The honest part, full fault tolerance for a streaming, stateful, expensive workload is genuinely hard, and most systems accept some regeneration. Admitting that, with the reasoning, reads as senior. Don't serve the same work twice. Layered caching, an exact response cache for identical prompts. Cheap but low hit rate. Prefix caching, many requests share a long system prompt, so cache that prefixes state and reuse it across users. Big win. And semantic caching for similar meaning prompts, highest hit rate but risky, because similar isn't the same. Correctness versus savings. 100,000 token context. Now cache memory really bites. One request can exceed a whole GPU's spare memory. Offload the cache to CPU memory, page it, or cap context, and summarize older turns. All trade-offs of quality versus memory versus latency. Deploy a new model version safely. Canary it. Route a small percentage to the new model. Watch quality and latency. Roll forward or back. But you can't hot swap weights on a live replica. You drain it, reload for minutes, then return it. So rollouts are slow and need spare capacity. And the CFO says the bill is too high. Batch harder, more throughput, worse latency. Our core tension returns. Model tiering. Route easy requests to a small cheap model, only hard ones to the big one. Quantization, run in lower precision, small quality drop. Spot GPUs for non-urgent batch work. Show you never stopped watching that utilization number. Before we recap, let me save you from the mistakes that sink this exact interview. Interviewers are watching for every one of these. Red flag 1, jumping straight to boxes. Drawing a load balancer before asking a single question signals junior. Fix, spend the first minutes on requirements and numbers. Earn the architecture. Red flag 2, treating it like a normal web service. Add a load balancer, add replicas, add a cache. That misses that this system is defined by GPU memory and utilization. Fix, name the real bottleneck out loud, early. Red flag 3, not knowing prefill versus decode. If you can't explain the two phases with opposite hardware profiles, you can't reason about any optimization. This is the concept. Fix, lead with arithmetic intensity. Red flag 4, buzzword dropping without the why. Saying I'd use continuous batching with no mechanism is worse than silence, The follow-up exposes you. Fix every technique, state the bottleneck it attacks. Red flag 5, ignoring cost. In this domain, cost is a functional requirement. Fix, estimate the fleet, put a dollar figure on it, treat every optimization as a cost lever. Red flag 6, no trade-offs, only answers, presenting one design as the answer. Fix, for each choice, name the alternative and why you rejected it. Red flag 7, faking certainty on the frontier, confidently stating exact numbers or a proprietary system's internals. Interviewers can smell bluffing. Fix, qualify honestly. Order of magnitude. Calibrated confidence beats false precision every time. The pattern across all 7. Reason from first principles, quantify, and defend trade-offs. Do that, and you're not reciting. You're engineering. Zoom out on what we built, and notice every box was a choice we defended, not a fact we recited. One GPU serving one user, burning money. We found the real bottleneck through arithmetic intensity. Prefill is compute-bound, decode is memory-bound. The KV cache shrunk with grouped query attention, computed cheaply with FlashAttention. Continuous batching over static for 3 to 5 times the throughput. Page cache to stop fragmentation. Chunked prefill and speculative decoding. Then we scaled out, disaggregated prefill and decode into separate pools for 2 to 4 times the cost savings, tensor parallelism inside a node, replicated into a fleet, routed cache-aware instead of naively, queued with priority and aging, auto-scaled around GPUs that cold start in minutes. And every follow-up, a trade-off. The 8 things to walk away with. 1. The bottleneck is GPU utilization. 2. Arithmetic intensity is the lens. Prefill compute-bound, decode memory-bound. 3. The KV cache is the resource you manage. Shrink it, compute it cheaply. 4. Continuous batching is the core win. 5. Disaggregate prefill and decode at scale. 6. Estimate capacity all the way to dollars a month. 7. Routing is cache-aware, not round-robin. 8. Everything is a trade-off. Name the alternative. Defend the pick. Master those 8, and you can rebuild this entire design on any whiteboard. But here's the thing. Knowing this and performing it out loud, under pressure, while someone interrupts you with "why not the other option?" are completely different skills. You can watch this 10 times and still freeze in the room. The only fix is reps. That's exactly what we built CreaKit for. Practice this exact interview, system design, and LLM engineering rounds, with an AI interviewer that pushes back with the follow-ups, just like I did, and tells you where your reasoning broke down. Links in the description. It's free to try. Design the system. Then go practice defending it. I'll see you in the next one.